Okay, so I wanted to make sure I went over the practice test with you. I apologize I couldn't do it live. This is a really good question that hopefully you're watching this on to make sure you got it right. It's not going to be a graded question. It was more of a completion assignment, but the one that's this week is a graded question. It's also being done on It's Learning, so it's a little bit different, so hopefully you're paid attention to that. But let's sort of get right into it. I'm not going to read everything for you because hopefully you did it. Well, obviously, pretty all you did it. But you're basically supposed to drive an expression for angular momentum, but in terms of h, right? So everything has to be in terms of h, and that's the important thing here. So here is our equation for angular momentum. We've got L equals I omega. Now, we actually are already given the I. It's given right up here. Okay, so what we do need is an omega. So how do we find the omega here? Well, angular momentum pairs really well with energy, and also that would be a good way to find our omega. So our potential energy plus our kinetic energy is going to equal our potential plus our kinetic. Now, you might ask a couple questions here. Mr. Cooper, why did you use I's here and not F's here? You used 2's. Why not use 1's and 2's? I could have used 1's and 2's here, but I did this for a particular reason. The initial, that's where you're starting from, right? But this is not necessarily the final. This is the height, basically, with respect to h. So I could have put an h there, but when I did that, it got really confusing with the h's in here, so I just used 2. But understand, this h is changing. Okay, so this h is going to be changing, but the important thing to understand is still, just like most of the time, all of the potential is going to turn into all the kinetic. Now you might be like, Mr. Cooper, wait a second, you just said that it might not be at the bottom, and I don't know if I said that or I said that in one of the other 40 video takes of this particular video I've made. So this h is not necessarily at the bottom, but you're measuring from this h. So whatever potential energy is from this h will completely turn into kinetic energy from this h. Now, if it's at the bottom, that's normal. But even if it's up here, if there's still energy down here, that's fine. You'd still have the potential energy left over that would turn into kinetic. But from this particular piece, it's like this. Even though this can be changing, this is like what you're measuring from. It's like not really your origin, but it's where you're measuring from. So although this h may not be all the way at the bottom, it's still where you're measuring from. So all of the potential based on that h will turn into kinetic based on that h. All right, so now we just sort of plug in our equations, and our potential energy is mgh, and then our kinetic energy is 1/2 mv squared. Oh yeah, 1/2 I omega squared, and that's important to understand. So we got this I omega squared in here. All right, why? Well, how do I know I have that? Well, because they gave you the I, so obviously it matters. Now, moving on, we're going to start plugging in what we know, and the only thing we know on the potential side is m. As far as the other side, we're asking for angular momentum. So that velocity isn't really going to do much for me, so I'm going to get rid of that velocity and turn it into its angular equivalent, which is r omega. Okay? And that is going to be plus 1/2 I, which were given to us, right? And then omega squared. Now, we want to combine these two things because obviously we need to first solve for omega here, right? So if I combine these two things, this is 1/4, right? And if I distribute this squared sign, I'd get r squared omega squared. Well, if this denominator is 4, this denominator has to be 4. So in order to get it 4, I multiply by 2/2, and I get 2/4 r squared omega squared, right? Now first, hopefully you've noticed there's an m here, and I can cancel those m's out. So I'm going to end up getting GH. But I've got this 2/4 r squared omega squared plus 1, in a sense, r squared omega squared. Well, what is 2 plus 1? That's 3. And what is, if you have a common denominator 4, it's 4. So hopefully you kind of figured out how we got to that step. So that's our common denominator. Our masses cancel out. I've got 2 r squared omega squared, and I have 1 r squared omega squared. Well, 2 plus 1 is 3, and I put that right there. Boom. So that's kind of how we got that one. All right, let's keep moving on. I'm trying to solve for omega, right? So omega equals this, right? No, because you had a squared there, so omega squared, right? Hopefully you kind of got that one there. Okay. Now, we know that L equals I omega. We talked about that in the beginning. So that equals mr squared over 2. Okay, that were given to us. That's given to us up here, right? That's given to us in the problem. And then it's times what we just solved out there. Well, let's just take a quick look at this thing to see what the answer is going to be. The 4 can be pulled out of the square root, right? So you'd have 2, right? And those 2's would cancel out. The r squared can also be pulled out as an r, and that squared sign, in a sense, are going to cancel out. So you're just left with mr, and then what's left in there? So mr square root gh over 3. And there is your answer. All right, so let's move on here. So is the angular momentum of the cylinder conserved? Well, I mean, no, it's not. So there's a couple reasons. You have obviously this I, right? And that's going to slow things down. But there's also something else that's acting out. There has to be friction. How do you know there's friction? Because it's not slipping. So there must be friction. And if there's friction, friction is a non-conservative force. So friction is going to cause a torque, an external torque in a sense, on the cylinder. You can also surmise that because they did not say friction, there's no friction in this problem, there always is friction in this problem. Now let's say your brain didn't go there, for instance. My brain actually went there. Why? I don't know why. It just went there immediately. If they mention, it says that without slipping, that means there has to be friction. So that's kind of how I got there. But there's another reason it's not. The angular velocity is changing with h. So the L has to be changing. I mean, you figured this out. As your h changes, this omega is going to be different, right? So your L, your angular momentum, which is basically mass times velocity in a sense, has to be changing, right? So if your omega is changing with h, your L also has to be changing. And that's pretty much that one. So angular momentum is obviously not conserved. All right, so let's move on. Now, a trick that I don't remember which guy said it, but think about your reasoning before you click here and then before you put on that. All right, let's move on here. So now we have this child's toy, rotational inertia of the toy around its center. Express your answer in terms of MR. So we got to derive another equation here. So we've got our I total. So if you remember, your total I is going to be the sum of all the I's, right? And instead of having this solid disk, now we have this thing. It kind of looks like a yo-yo to me. So that's important to understand. So here we have two I out. Wait, why do we have two of them? Why do we have two I out? Well, think about this. You have one outside disk there, and you have one outside disk there, right? So that's two outside disks, okay? Plus I inside. So if you were to sum all of the I's, these are things that are rotating, there's in a sense three of them. 1, 2, 3, like three of them, right? So that's 2, and that's 1 and 2, I'm pretty sure is 3. Right? Yeah, okay, I don't need a calculator for that. Okay, we're good on that one. So there you go. We're still using the same rotational inertia, though, which is kind of nice. So equals 2 mr squared over 2, out, that's the outside one, right? And plus mr squared over 2, that's the inside one. Okay, so now I'm just going to distribute the 2 here from here, right here. I'm going to distribute this 2 right here. And basically the 2 gets in there, and it goes into 2r squared over 2. Close parentheses. Wait a second. I don't understand, Mr. Cooper. Please explain. Okay, let's take a look here. Child's toy comes with 3 narrow cylinders. They're constant. Cylinder mass, radius r. Each of the 2 outer cylinder has a mass of r and a radius of 2r. Okay, so that's me not distributing the 2 per se. That's me putting in this 2r. That's the outside one, and the inside was just the normal r. So plus mr squared 2, and then I can sort of do some actual distributing. Well, obviously, the 2's cancel out, right? So these 2 cancel out. This 2 becomes a 4 and r, and then squared. There you go. Plus mr squared over 2. So my I total is 9 halves mr squared. How did you get 9 halves, Mr. Cooper? Okay, so this is 4 over 1, but in order to add it, you have to have a common denominator. So how do I get 4 over 1? I need to multiply by 2. So I'm getting 8 over 2. Well, 8 mr squared, and then basically there's a 1 here, right? Plus 1, and 8 plus 1, 8, use your fingers, 9, and then you still have your combinator of 2, mr squared. There's your I total. All right, let's keep going. All right, D on the dot below. So again, this is not something you'll have to do in the problem. However, and I modified the questions now so they're going to be more like it. You may not actually have to draw this on your test, but you may have to describe it. So how would you describe this? Well, the force weight or the force gravity is an arrow going from the center of the block, it's not exactly the center, straight down. Excellent. Force normal. Okay, so the force normal is going from the center of the block, but it is perpendicular to the surface. So these are key terms you have to say. And there's a force friction going up. Okay, the toy is placed on the dot below, blah, 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 horizontal only, the central contact with the side above. The toy rolls without slipping. So it rolls without slipping, so that's a good thing. Means there has to be a force friction going up, right? So the force friction then is going up the ramp parallel to it, basically from the center, sort of. Okay, there we go. Now, derive an equation for the linear acceleration of the toy as it rolls down the track. Express your answer in terms of mr theta, it's interesting, and physical quantities as appropriate. So we take a look at this thing. F equals ma. That's like Newton's 13th law, right? Yeah, something like that. Okay. So hopefully we know that by now. So 3m. Well, wait. Why is it 3m? I'm gonna let you figure the 3m out on your own. Okay. So we'll talk about that later. So 3m g sine theta. Right? The 3m's because there's like 3 blocks, right? Hopefully you can get that one. Yeah. Okay. So, and then g sine theta is your a. So it's the gravity pulling it down, right? Minus force friction. Right, so this is the gravity part of it, and then there's the force friction part of it. And the sine theta is because you want the opposite side of it. Equals 3ma. The mass is 3m. Go back to the last problem if you need help with that. Okay, moving on. Okay, so torque equals I alpha. Now we know there's torque involved in this, and that's gonna affect the acceleration, obviously. So torque equals I alpha. So force friction, the torque is going to be force friction times the radius. That's the distance it's from there, right? Equals 9/2 mr squared. Where'd that? Oh, that came from the last question. That's right. Okay, I remember that. Yeah, I got that. That's the I total. And then your alpha is a over r squared. Remember, this wants an explanation for linear acceleration. So anytime you have this alpha, you want to get rid of it. And just like we had to do with the velocity, got rid of it by omega r. Well, we now got rid of the alpha, and we get rid of that by a over r because we're talking about linear here. Okay, so I'm good here. I'm good. So, okay, anything else acting on the torque? Okay, no. Okay, so force friction is then going to equal 9/2 ma. Wait, Mr. Cooper, what happened to the r? No, sure, we'll talk about that. Sure. Okay, so basically there's an r in every term. So cancel and cancel the squared. And then this r and this r, well, yeah, they would cancel each other out. Boom. And then you're left with 9/2 m times the a. Boom, shakalaka. Okay, so now 3mg sine theta, that's this right here, right? That's this bad boy right here, right? Okay, good. Minus, and now we got force friction, which is that bad boy right. Okay, I'm with you. Equals, yeah, 3ma. Okay, what am I solving for again? A. That's right, I'm solving for A. So 3g, so wait, where'd the m go? Well, there's an m in every term, right? So we get rid of that. 3g sine theta equals 15 over 2a. How did he get 15 over 2? I ain't even doing this one with you, okay? You got to figure that one out on your own. I'm not dealing with you with that one. Just common denominator nonsense. A ends up equaling 2/5 g sine theta. Boom. If you think that's a mistake, show me. That's all I got to say to you. Show me. Show me the money. Well, I mean, don't show me. That sounds stupid, but you get the idea. How did he get that? I mean, I mean, that's a 9, right? Right? Okay, that's a 9. I just don't. Yeah, figure it out. Moving on. 9, right? 9, and then to get that, it's common out of 2. I'd multiply by 2, so 6 and 9, 15. Boom. Obviously, it's been a long day. Determine the force friction exerted on the toy as it rolls. So this really answer has to be basically from your part di, right? So force friction equals 9/2 m, boom, 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 boom. And that's basically from the last part. And then you just have to work some stuff out, and bam, that's all that one is, okay? I mean, there's nothing really crazy. How'd you get the 9/5, Mr. Cooper? Yeah, I'm not even going to help you with that one. That's all on your own. Okay, and our last part, E. The toy reaches the bottom of the incline and rolls at a constant speed V along the horizontal section, blah, 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 blah. Derive an expression for total kinetic energy. All right, kinetic equals KL plus KR. What's the L and the R stand for? I'm confused. I'm going to let you figure that out on your own. 1/2 mv squared plus 1/2 I omega squared. Yeah. Linear rotational. Okay, there we go. K equals 1/2 3m v squared. We know that one, right? Okay, good. Plus 1/2. Yeah, that's the I total omega squared. Okay, so far so good. Total kinetic energy equals. So, how did you get the 3/2? Yeah, 3 times 1/2. Okay, 3/2. There you go. Moving on. Plus, okay, people. Yeah, there we 1/2 of 9/2 is 9/4. Wait, why'd you get rid of the omega squared? Because I got to put them somehow together, and it wants it in terms of V. Do you see an omega in this thing? No. It has to be in V. So we had to get rid of the omega, and that's V over R. And it's just algebra. I mean, seriously. 2, 4, so times 2, 6, 9, 15. Boom. Okay, there you go. The rest, seriously, you should be able to do that on your own. All right, hope that helps. Hope you did well on it. Feel free to talk to me about it. Talk to you later, dudes. Bye. And dudettes.